Hello, for this video lecture we're going to be talking about the conservation of energy for a system of particles. Alright, so working energy for systems of particles. So far we've defined our system as being a single particle, single body that we're going to work on, where the work done to this particle is going to cause some change in energy of the particle. Both kinetic and potential energy is going to be changed. So if we redefine our system to include multiple particles, we can still apply the same formula we used before. The work done to the system of particles will be equal to the change in kinetic energy of the system of particles plus the change in potential energy of the system of particles. So still one equation, but we've got multiple bodies tied up in our system now. Alright, so to find the work done to the overall system, we simply need to sum up all the work done to each particle in the system. So the total work would be the work done to particle 1 plus the work done to particle 2, so on and so on. However many particles we have, we just need to add them up. Same thing for energy. To find the change in kinetic energy total, we would find the change in kinetic energy to particle 1, the change in kinetic energy to particle 2, and so on for each particle. And then potential energy, either gravitational and or our elastic potential energy, we simply find the change in potential energy for each particle as a piece. So all of these things get thrown into a single equation, that W equals delta KE plus delta PE equation we used before. Alright, so why would we use this? Well, in analyzing a system of particles, the reason we do this rather than analyzing each particle separately is because we can ignore the work done by internal forces in our system. So if we have these internal forces, if we kind of set the boundary to the system to have that not cover that interface, we can ignore them. All right, so the reason we can ignore the work done by internal forces is because these work terms are always going to cancel each other out because of Newton's third law. So if I've got two particles tied together with a cable, the tension is always going to be equal and opposite. Anything that is tied together with like a pin joint, the forces are going to be equal and opposite. Because the forces are always equal and opposite, force times distance, and if they're tied together that way, the displacement is going to change as well. They're always going to add up to be equal to 0. Since they add up to 0, we ignore them. All right, so an internal force specifically is any force exerted between two bodies that are within our system. External force is any force exerted by something outside the system onto something inside the system. So one of the bodies in our system. So at this example here, we've got particle A, particle B. Our system includes both of those boxes. The tension force here is an example of an internal force because it's tying those two boxes together, and you can see that they are not necessarily equal and opposite in this case, but the displacement, the tension is going to be tying those two things together. The friction force, on the other hand, so the friction is applied from the base of this platform onto box A. And so since the interface is between box A and the tabletop, A is within our system, this platform is not within our system, that's going to be an external force on our system. So we do need to worry about the work done by that friction force. We don't need to worry about the work done by the tension forces. Alright, so with all of that, one potential pitfall is still, with the work and energy method, we only have a single equation to work with. So in order to determine the overall relationship between position and velocity, so we're often going to need to use constraint relationships. So this can be just the straight up kinetic or kinematics relationships, and since we're often dealing with cables in these systems, we're also going to talk about dependent motion analysis quite often as well. So if you use these constraint equations along with your conservation of energy equation, we often get the amount of equations we need to solve for all of our unknowns. Alright, so overall, the process for these problems, what we're going to do, it's still a work and energy problem. So solving a work and energy problem involves 3 steps, carefully accounting for the factors at play between some initial state and some final state in our system. We're going to, number 1, set up a diagram showing the initial state, set up a diagram showing the final state. We want to identify any external forces that are going to do work on between the two states. So again, we can ignore those internal forces. We want to identify known or unknown velocities in each state, identify the changes in height if applicable to our system, and identify the x values if we've got springs in our system. So those x are going to be for elastic potential energies. So put all those things into our diagrams. Next, we're going to use the diagram to put together the single conservation of energy equation. Work is equal to delta KE plus delta PE. And again, since it's a system of particles, it's going to be the sum of all the works, the sum of all the kinetic energies, the sum of all the potential energies in each of these pieces. So if we have more than one unknown in the resulting equation, we need to come up with some extra equations. So use your kinematics, use your dependent motion analysis to come up with some extra pieces, relate, maybe two of the unknowns are related to one another with kinematics. So once we come up with those equations, last step is just the algebra. So we need to solve the equations for any of the unknown quantities in our final resulting set of equations. So with that, that's all I have for today's video lecture. Thank you for watching and hope to see you again.